the moon's slow drift away from Earth, exploring the causes and implication of our moon's shifting orbit? The speed at which the moon is moving away from Earth could affect life on the planet, but this could take billions of years to happen, writes space scientist Dr. Maggie Adderin-Pocock. It's easy to take the moon for granted, even on a clear night when it can light up the sky. It really feels as if it has always been there, just as it is now, throughout history. It is thought that the moon was formed when a protoplanet about the size of Mars collided with the early Earth around 4.5 billion years ago. The debris left over from impact coalesced to form the moon. Computer simulations of such an impact are consistent with the Earth-Moon system we see in the 21st century. The simulations also imply that at the time of its formation, the moon sat much closer to the Earth, a mere 22,500 kilometers, 14,000 miles, away, compared with the 250,000 miles, 402,336 kilometers, between the Earth and the moon today. The moon continues to spin away from the Earth, at the rate of 3.78 centimeters, 1.48 inches, per year, at about the same speed at which our fingernails grow. Without the moon, the Earth could slow down enough to become unstable, but this would take billions of years and it may never happen at all. If we first think about the moon in relation to the Earth, we can explain how it appears to travel across the sky over the course of a night, and why it rises and falls at different times and in different locations. Just like the sun and the nighttime stars, the moon's apparent rising in the east and setting in the west each day is not from the moon's orbit around the Earth, it's from the Earth spinning. The lunar orbit is slower and harder to see, but you can still spot it. By looking at where the moon is in relation to stars in the background one night, and then comparing to where it is several hours later or on the next night, you'll notice it has moved east. This movement is from the moon's orbit, which takes 27 days, 7 hours and 43 minutes to go full circle. It causes the moon to move 12 to 13 degrees east every day. This shift means Earth has to rotate a little longer to bring the moon into view, which is why moonrise is about 50 minutes later each day. The migration of the moon away from the Earth is mainly due to the action of the Earth's tides. The moon is kept in orbit by the gravitational force that the Earth exerts on it, but the moon also exerts a gravitational force on our planet, and this causes the movement of the Earth's oceans to form a tidal bulge. Due to the rotation of the Earth, this tidal bulge actually sits slightly ahead of the moon. Some of the energy of the spinning Earth gets transferred to the tidal bulge via friction. This drives the bulge forward, keeping it ahead of the moon. The tidal bulge feeds a small amount of energy into the moon, pushing it into a higher orbit like the faster, outside lanes of a test track. This phenomenon is similar to the experience one feels on a children's roundabout. The faster the roundabout spins, the stronger the feeling of being slung outwards. But the energy gained as the moon is pushed higher is balanced by a reduction in the energy of its motion, so an acceleration provided by the Earth's tides is actually slowing the moon down. While 3.78 centimeters may not seem like much, this small difference over a long enough period of time could affect life on Earth, making the planet slow down. On early Earth, when the moon was newly formed, days were 5 hours long, but with the moon's braking effect operating on the Earth for the last 4.5 billion years, days have slowed down to the 24 hours that we are familiar with now. And they will continue to slow down in the future. We can see some evidence of the slowdown in the fossil records of some creatures. By looking at the daily growth bands of corals, we can calculate the numbers of days that occurred per year in past periods, and from this we can see that days are getting longer, at a rate of 19 hours every 4.5 billion years. The length of a day, or in other words the rotation speed of the planet, plays a big part in its stability. Just like keeping a plate spinning on a stick, the key is to have the plate spinning fast, as if it slows down it crashes to the floor. In a similar way, as the Earth's rotation slows down, our whole planet may start to slowly wobble, and this will have a devastating effect on our seasons. We have the seasons we currently do, due to the Earth's tilt at an angle of 23 degrees on its axis. During summer, the northern hemisphere is tilted towards the sun, so we get longer days and warmer weather. However, in winter the northern hemisphere is tilted away from the sun, giving us shorter days and cooler weather. If this were to change, and the Earth became unstable, then parts of the world could experience much greater temperature swings than we are used to through any given year. With freezing Arctic temperatures in winter followed by blazing hot temperatures in summer. To grasp why the moon's appearance changes, we need to bring in the sun. Like the planets, we only see the moon because it reflects the sun's light. And just as we have half the planet lit and the other in darkness at any one time, the sun is always shining on half the moon. This means there is no dark side of the moon, just a side facing away from the Earth. From Earth though, it looks like the moon goes through different lit-up phases. If you are in the northern hemisphere, The moon's right side grows with light from a crescent to a semicircle and then a gibbous, more than a semicircle but less than a full circle, shape until finally it becomes a glorious full moon. This process is called waxing, and takes about a fortnight. And then the opposite happens on the left side as the portion lit up shrinks to nothing, known as a new moon. This process is called waning. As the view from the southern hemisphere is the other way around, the moon waxes from the left and wanes to the right. This shows clearly that it's not the moon but our vantage point on Earth that changes, and explains the phases we see. For instance, a new moon happens when the moon is between the Earth and the Sun. The whole of the far side of the moon is in sunshine, but we see, or rather don't see, the side that's in full shadow. During a half moon, we see half of the moon's day side. The other half is shining out in the opposite direction to Earth. The fact we can sometimes spot a faint outline of the dark sections of the moon when it's not full is because some of the light from the sun is bouncing off Earth and lightly illuminating our lunar companion. The effect is called Earthshine. Mercury, Venus and Mars also have phases similar to the moon which can be spotted at certain times with a telescope. And the Earth has phases too. When Apollo astronauts looked back on Earth from the moon, they didn't just see a globe. They marveled at crescent, gibbous, full and new Earths depending on which phase our planet was going through. So, the appearance and position of the moon change based on the way the Earth and moon orbit the sun and the fact that the Earth spins round once every 24 hours. But with all this spinning and orbiting, it begs the question, why don't we see the moon spinning too? In fact, though we always see the same side of the moon is spinning. This is no coincidence. It's called synchronous rotation, and is a result of the gravitational tug-of-war between the Earth and the moon. In the distant past, the moon was rapidly spinning close to the Earth, but then gravity from Earth's huge mass began to take effect. Tidal forces allowed the moon to drift away from the Earth in its orbit and slowed its spin. Eventually, the moon reached a point where one side was always facing the Earth. The same forces that caused the moon to always show the same face to Earth continue to influence the moon and Earth today. The moon still drifts further away a few centimeters a year. What is more surprising though is that the moon and Earth's gravitational tug-of-war is slowing down the Earth's rotation a tiny bit too. If it were not for the sun's eventual demise, this would continue until the Earth and moon were tidally locked. In this situation, both the moon and Earth would spin at the same rate of 47 days, showing the same face to each other for the rest of their existence. As humans, we have the ability to adapt to our local surroundings to meet our needs. If humans are still around when and if it happens, it is quite likely we would survive these massive changes with air conditioning in the summer and a lot of heating in winter. Like, comment, share and subscribe to my channel.